Hope that you're enjoying the day so far and the great weather in January here. So, great talk before me. Professor Howe mentioned a lot of things. When it comes to healthcare, there are so many challenges, at least I see from, in my opinion. I mean, I was going to ask a question. What about that clinical knowledge, that how do you feed it into these models? Yeah, not yet. So we talk to clinicians, I talk to clinicians almost on a daily basis to try to fix how these models that we develop work. Sometimes it does work on some population, it fails on others. So there's so many challenges that we still face, and I think we still have a lot more to do to improve what we do when it comes to modeling healthcare data. Okay. So while they're loading this one, so I work in AI in healthcare, and in the past 18 years I've been doing that. So I did my PhD in fetal health, then followed by several years of work on ultrasound images. Then when I moved in here to Embedded AI, I lead the, we're good? Can you just click on the presentation? There you go. Yeah, there you go. Thank you. So what I do is, so I lead a team of roughly 30-ish people to work on a diverse range of problems. The majority of the projects are on medical imaging, a little bit of the projects on non-imaging, but in general, the problems that I focus on are on first, fetal and maternal health, second, cardiovascular problems, and then oncology problems. So I work on not a lot, but probably 2 or 3 different cancers. And then the third part is on pulmonary diseases. In general, these are the clinical problems, but I focus also on the technical aspects. So my team and I try to understand the generalizability, reproducibility of these models, the generation, so the diffusion models, and how you can generate data from data. That's when it comes to healthcare, it's much more complicated, and so on and so forth. A little bit of my team work on non-imaging data, and I'll touch on that later on. So before I put these slides, and I know it's a lightning talk, so I just thought, okay, what shall I present? I don't know the audience very well, so I thought, okay, I'll just make it very high level. First, I'll give you a glimpse of what we do in the group, and then I'll talk about a concept that I always ask myself about. Okay, currently, everyone in my domain, we use deep learning to analyze medical imaging. So one question I always have, what about classical statistical model? Do you still need it? Is this like really deep learning will just fix everything for us? We just put data and get answers. So that's a question I'll try to talk about today. I don't have an answer to it. I have some thoughts, which I'll share with you. And the other thing I thought I'll tell you about is one project where deep learning didn't work. It did not work, and even with lots of data. Okay, if this works. Stuck here as well. There you go. Okay, now it's working. Okay, so this is thanks to all my team members who are working hard on many different problems. And if you're interested, you can find our website. My team and I, the group name is called Biomedia, from Biomedical Image Analysis. I did mention this slide where my team and I focus on different aspects of healthcare, from fetal to cardiovascular to brain to pulmonary and so on and so forth. From non-imaging problems, so we work on a small number of problems such as electronic health records. Sorry about the format. It doesn't seem to be loaded the same way that it loads on my computer, at least. So electronic health record is a big thing that we work on, where we have data coming from patients. They're not imaging, but they're just diagnostics, lab results, so on and so forth. The question is, how could we use it? And I would say in the last 3 years only I started to look into this. Before that, I was only imaging person. But that was really probably naive of me, because there's so much information in the history of the patient that can change how the modeling imaging data could be significantly impacted. Other part of my work focuses also on a bit of genomics, but I'm not going to talk about that today. So The question I always ask myself, I don't have an answer, is deep learning, how does it differ from these statistical classical methods? I'll tell you an example. When I did my PhD, spent so many years in doing feature engineering to ensure that I extract enough features, good features, that when I feed it to random forest or SVM or even basic logistic regression, I get good results. And I would say most of my PhD was on really the data analysis, as Professor Zhao mentioned. We spent a long time doing that. And then I finished my PhD, thankfully, but then deep learning came to the equation. And I was a postdoc at that time, and then my supervisor said, can you repeat one experiment of what you did in your PhD with AlexNet at that time? And I put some data in, and I remember from my PhD, well, the best result I got was probably 81 from a random forest model with lots of feature engineering. And then I put it in AlexNet at that time, and I got 91. So a 10% jump. I was very sad. I was very sad. 3 years of working hard, and then within a week, I managed to get a much better result. And I did publish that in great places, but still, this is what deep learning, I hated it at the beginning, but now we're all working with deep learning. So it is a deep learning model, a statistical model. So we know, for instance, the CNN generates a probability if we're doing classification, but that's not a really a density function. It's just a softmax that generates probability. So the question I always ask myself, is it part or not part of statistics? And the other question is that, what about the other methods? What about SVM, random forest, logistic regression, and feeding that into deep learning? Does that make these deep learning model better or maybe more explainable, because it's really hard to explain what's inside the box? And then I kept on looking into that. So for instance, this is a slide, a figure from a book that just tries to say where everything in the equation. You might agree or disagree with this. I do disagree a little bit with that. But if you look at it, it just puts statistics on the side, while you see other things like deep learning within machine learning, within neural network, and so on and so forth. And there's no proper overlap. I looked into other sources. This is not the source that I disagree with this one, but I put it here to question your mind. So the overlap is different in my opinion, but I want to put that in because there's so many argument, I would say, between what is statistics when it comes to compare to deep learning and neural networks. So to me, if I want to redraw this one, I would probably expand that orange box and just keep it to overlap with even all the way to deep learning, but not completely within deep learning, but at least a good part of it. Okay, so what is medical imaging? Professor Zhao mentioned that a lot. In general, it's data that we acquire to get access to look inside our human body. So this is, for instance, a human brain and it's an image, it's a 2D slice coming from a 3D image, and each point is a pixel that has a value, right? So why is it complicated? Why is it different than natural images? There's so many reasons, and Professor Zhao mentioned a few. For instance, we work with multimodality data. So if a patient comes in today for a problem in the brain, you're likely to start with a CT scan. It's cheap compared to MRI, fast. It has some radiation, it has advantages, disadvantages. Didn't work, you didn't see the problem, you probably go for maybe CT angiography if there is a problem, leakage in the brain or rupture. If that doesn't work, probably MRI or maybe MRI before, depending on the condition. So in healthcare, there's so many different imaging modalities, which makes it very complicated when you assess a person's disease. So that's one thing. But the other thing is, it's not just a 2D image. It could be 2D, 3D, 4D. So I worked in many different types of data, and sometimes even 1D if you want to consider ECG. It's not imaging, but it's also a very important modality that we work with when it comes to healthcare problems. So let me ask you this question. What is that? What do you think that image is? I'll just give you a hint. It's two images of part of the human body looking from two different perspectives. What do you think this is? Spine. So, and what is it actually looking at? There's a bright region right near the spine, right? What is that? That's a tumor. And that's what we call the head and neck cancer. What's this imaging modality called? Do you know? Anyone? It's a PET scan. PET scan usually is a type of scan where you inject a radio tracer into a human body, and because that radio tracer is like sort of like sugary, abnormal tissue will observe that, and then when you image the patient, you will see that abnormal regions. Anyway, so the real image from CT is that one. You can now really see the brain and the spine and so on and so forth. So the top one is a CT, the bottom one is a PET. To verify head and neck cancer, if I'm a doctor, I need to get these two scans. These are 3D scans, by the way. They're not 2D. I'm just showing 2D here. So why do they do that? Because they want to look at the cancer, quantify it, measure it, stage it, because all these decisions or all these metrics help the doctor make decisions. What are the right treatment plans? Shall I say stage 1 or stage 2 or stage 3, and so on and so forth. So we did a set of studies on head and neck cancer. That's why I picked this study, because we did a lot of publication on this domain, where one major question we try to answer is a patient comes in today to the doctor. Doctor looks at this data. One question a patient will always have, especially in late stages of cancer: what's going to happen to me? Am I going to die in 6 months or 1 year or maybe 10 years? So survival. And that's a regression problem for us. Like if we have data, we can regress for that. But it's not really an easy task. So the reason I put that in is I want to mention our work. We started in 2020 and then all the way until now. And we were looking mostly on, could you look at imaging data alongside electronic health record and other type of data for patient with cancer and tell what is the survival rate? When will this patient die, in other words? So it's a tricky question because you have data, but how could you do that? So we looked into first, let's use the imaging data. See, that doesn't work, it does work. And see if we can use PET and CT and just predict what's the next probability of death. And that didn't work. Imaging data doesn't actually give you good enough information about that. PET gives you, CT doesn't give you much. But then when we augment that with electronic health record, some basic information about this patient, then things started to work. But the other question we wanted to do is we want to work on deep learning, but these sort of electronic health record, because if you put them in a deep learning architecture, it doesn't work very well. You have to really understand what data you're working with. So what I'm trying to tell you here is that in my opinion, the best solution that we managed to bring is to develop a hybrid model that uses a classical machine learning with a deep learning model to be able to analyze multimodal data, imaging and non-imaging data. So in this scenario, it was like just a CNN at the top and Cox hazard proportion model, both fed into, if you look at the top part, is also the outcome of the CNN. We did not send it to a softmax, but we send it to a multi-task logistic regression. And we found that to be a better approach than just do a basic regression loss function, like a mean square error or something like that. So what I'm trying to tell you here, let me just show you also the video, is for problems such as survival prediction, a hybrid model that uses classical statistical method and maybe a deep learning method that focuses on the images is likely to work better than just using either, each one of them separately. So that's the tumor in 3D. So we extended this work, and Nu'man is here, is my postdoc working with me on this. We published a few papers on that. This is a 2022 papers in Mikai where we saw, okay, now let's do something more things. Let's do what the doctor do. The doctor actually looks at the data, quantify the tumor, measure it, quantify some metrics out of it, and then based on that, make a decision. What's the likelihood of death? What's the likelihood of recall of the cancer, and so on and so forth. It's a complicated figure, but what I want to show here that we only managed to get to really good results on multimodal data when we start to augment classical statistical methods with these deep learning methods. Here we see this, we change the CNN to a transformer, and then we still use MTLR to be able to do segmentation and as well as regression. Okay, I'm just conscious of the time. That's why I'm going to close up here with a few questions rather than, so I call it take-home message, but I left it as questions for you. So the first question is on these deep learning models. Which one is better? Which one shall I use? Is it a hybrid model that we'll be using? In my opinion, it depends on the problem. So if we're doing just image segmentation, it turns out there's these deep learning methods starting from UNet all the way to more advanced version, but UNet is probably still the most powerful, very powerful method. These things will work well on imaging. But when you start to have multimodal data, really, just basic deep learning model may not be the best option. In fact, for some problems, it's an overkill. I don't have a slide for that, but we're working on Alzheimer's disease on a study where we actually showed just analyzing the MRI directly doesn't help. We have electronic health data. So what we did is we get the segmentation masks of the different structure of the brain, but then we compute radiomics features, some basic features. Then we feed that to just methods such as boosting or XGBoost or other method, and it works as good as, even better in some cases, than deep learning models. And the last question is that, this is what I just mentioned, is like, do we really need to learn from images directly, feed it into a CNN or a deep learning model? In my opinion, in some cases, yes, in some cases, no. So you have to understand your data before you make that decision. And with that, I'll finish. Oops. Sorry. And thank you very much. I'm not sure if we have time for questions.
I think we have time to take one or two questions. I can shout. Yeah. How are you getting measures of uncertainty? How are you calculating? I love your hybrid model. I think it's fantastic. Personally, I think it's great. But how do you think about uncertainty and talking about the uncertainty to your partners?
Yeah.
Like the healthcare?
It's a very good question. We study that as well. Like how do you estimate uncertainty when you make a decision? So there are different ways you can measure that, but currently what we're doing is we're looking into when you have a tumor that you want to segment, and the deep learning models or the algorithm is giving you segmentation. We're studying that in the sense where you have multiple doctors already segmented the tumor and try to measure the deviation from each one to come up with methods. So the best way we do it now is simply by understanding how doctors are different. Because uncertainty is also, so it comes in healthcare, it comes under subjectivity as well. Because if I ask, in the head and neck cancer, I think we did a study on that, but I don't have the numbers. But let me give you another number. In segmenting brain structures, a brain tumor, doctors will actually agree on approximately 80% of the time, if you bring two fantastic doctors. So there's already subjectivity in segmenting or figuring out where the tumor is. So we follow similar paradigm where we have data where we have multiple annotators, and we try to measure their uncertainty. And we say, if this deep learning model is actually within the bounds of two humans, two experts, then we're good. Otherwise, we're not.
I don't know this cancer very well, but my first question is that why there's no treatment? When the cancer is diagnosed, and then the first thing a medical doctor will make a decision on is come up with the right treatment, is radiation, surgery, or something. Why this information is missing in the prediction model? I mean, I know that you mentioned a few like demographic model or clinical variables, but I think the treatment or this cancer cannot be treated. I have very limited understanding about this cancer.
So
but anyway.
The question is why treatment is not included when you train these
Right, I think
models.
that will be a very important driving factor for survival.
I agree with you in the sense that depends the question that we're trying to answer. Here the question we're trying to answer, could you do that? Could you predict survival just right when you get the data before any intervention happens? So this data that we worked with doesn't have, all the images has been acquired before any treatment. Okay, so that's where we want to answer. Once, I agree with you, if you have this sort of data after specific treatment, feeding that to a model, that will be a better approach.
Follow-up question on that. Yeah, so just curious, for the AUC then, have you compared with other well-known markers for head and neck cancer, for example, HPV status, positive and negative? So I'm just wondering how much does PET scan add to the markers that are currently used in the clinic?
So I don't have a specific number to answer that, but we know that PET scan adds significant help to the doctor to make sure they can quantify the cancer. From the CT alone, you cannot really see the cancer much. And the other thing that PET scan adds significant help is that lymph nodes. So when the cancer is spread to lymph nodes, it becomes very tricky to see it on any imaging modality except the PET scan. So I don't have that number, but we know that it's a clinical standard that if a patient comes with a head and neck cancer, they go for a PET CT scan. By the way, it's now, with the current technology, it's one scanner. It gives you classical information, and it's quick to do, and so on and so forth. But as a next stage, you go for that. It's similar like what we do like in prostate cancer. You do prostate cancer, you do blood test to measure the antigen, prostate antigen, PSA, and then but that we know it's not really very specific. It has 75% false positives. So what they do after that is to go for MRIT2. So we know imaging usually give you a much either more specific or sensitive, depending on if we know PSA is great, but it's really give you lots of false positive, and many people end up having biopsy for no reason.
Yeah, I just quickly want to follow up Peter's questions. So predict the patient survivals is interesting, but ultimately we want to understand what we can do for this patient.
True.
The predictions and the variable features for the intervention, that's very different things. So have you ever done some work? What the treatment can better helping this patient?
No, that's a very good point. No, we haven't done that, but ultimately you want to use this information to help with the improving the outcomes later on. So my team and I, we didn't touch into this yet. Hopefully in future. Okay. Thank you very much, everyone. Thank you.
I know that you need to go teaching, so thank you so much for. Okay.